All right, I want to talk about Exemplar 2 for solving using velocity time graphs. Um, and this problem, when you first look at it, you say, hey, look, it's very similar to the last problem, isn't it? If a toy car or car goes from this speed to this speed with a constant acceleration and a displacement of the so much, how much time does it take with acceleration? You say, hey, it's the same setup, isn't it? So you would anticipate that we'd use the same technique. But there's something kind of tricky about this one that makes it a little more challenging, and I want to make sure that you're aware of that. So, taking a look at this, you say, first off, can we graph this? And you say, of course we can. We go from negative 12 meters per second to 4 meters per second. So we'll start here at negative 12 velocity axis and ending at 4 meters per second. We'll say that's here. Constant acceleration, again, means that we have a constant slope on our VT graph because the slope of a velocity time graph is acceleration. So that will look like this. Shunk. Right? Something like that. That's our graph. And so you'd say, well, that's the velocity time graph. We want to find the time it took and the acceleration. We're going to solve this. Again, we could solve using formulas, which I think in this case would actually be a lot easier. But we're going to solve using the graph because we want you to understand these techniques and using graphs. And sometimes we'll just give you the graphs to start. So looking at this, you say, there's my graph. I want to find the time that it took. And you say, well, that means we're trying to find the time. Maybe I'll go ahead and mark it here and say, we're trying to find the time there, right? And you say, well, we're going to go ahead and use my relationships. Again, we know two things about VT graphs. We know the slope is the acceleration, and the area between the line and the time axis is the displacement. They gave me the displacement here, so I'm going to try to use that to help me solve the problem. So first I'm going to represent it graphically. The displacement is the area between the line and the time axis. So you're like, okay, well that's going to be this area here. Shunk, 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 shunk. You say, but also the area here, chunk, 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 chunk. Always between the line and the axis, okay? We're not taking areas up here or down here. It's always going the area right there from the line straight to the axis. Okay, so that's it. So you say, hey, this area, it's two triangles. So you might say, hey, I know then that my displacement is the area of this triangle plus the area of this little triangle. You say, I know how to find areas of triangles. I understand that that would be 1/2 base times height of that triangle and 1/2 base times height of that triangle. The displacement they told me was negative 20, 1/2, and you're like, okay, well the base of this triangle, okay, I don't know how long that is. So I might just give this time here, I'm going to give that a name, okay? Don't just say, oh, I don't know it. We got to give it a name, a variable name, assign a variable to it, so then we have something to help us solve. So what I'm going to do is I'm going to call the time to here T1, and then I'll call the total time to here, this coordinate on this axis, I'll call that T2. So that means the base of this triangle is T1, is this length here, right? And the height is, and you say, well, I want to make sure this area gives me a negative area because I'm below the axis. So that's going to be a height of negative 12. I should have a negative displacement when I have negative velocities. So that negative sign is important. Okay, now the other triangle. So that'd be 1/2 its base. Well, its base, how long is this? If the time here is T2 and the time here is T1, this base length is T2 minus T1. And the height of this triangle is 4. All right, and that will give me my displacement. You say, except because I had this crossing the axis there, I've got these two different times. I've got two variables. I got T1 and T2. And so I need another formula, another relationship between those variables to help me solve. You say, well, where am I going to get it from? Well, the other thing that we know about VT graphs is that the slope is the acceleration. And so we can write equations for the slope of this line. We're going to use those to help us solve. So we're going to come back to this in just a minute. First, we'll do some slope calculations. I'm just going to do them up here. Hey, I know that the slope is the rise over the run. Now, my goal here, my immediate goal, is to try to find a relationship between the two t's, between this length and this length. And I can start finding those by looking at slopes for just these segments. So I might first solve for slope from when the velocity is -12 to when the velocity is 0, and that means the time would be t1. And so I do slope is rise for run. So my slope, which we know is going to be the acceleration, is my rise. It's going up 12 meters per second, and my run, which is a time of t1 seconds. You're like, well, did this help? Well, I just introduced, I got another equation with t1, but I introduced another variable. Now I have 3 variables, t1, t2, and a. And you're like, well, that's not that helpful. But hang on there. We can use this formula again for this segment. So if again I use slope is rise over run, and knowing that that slope is the acceleration, my rise here is 4 meters per second, and my run is, well, how long is this? If this whole thing is t2 and this is t1, then that run is t2 minus t1. And this is where something nice happens. I have a system of 3 equations with 3 unknowns, t1, t2, and a. So I can go ahead, I can solve. What I'm going to do is I'm going to get rid of this t2 minus t1 business. You see how this is a equals this and a equals this? I can combine then. I can substitute through a. I can say this is equal. If a equals this and a equals this, then this equals this. So I could use 12 over t1 is equal to 4 over t2 minus t1, right? A is this, so this is this. Let me get t2 minus t1 by itself. I'm just going to do it that way. So if I rearrange this, you know, I like to do, my middle school algebra teacher used to call this means extremes. This times this equals this times this. I don't know if that's what this is really called. He also said the math teacher before him used to call it kitty wonkus. But anyway, the point is this times this equals this times this, and then I can rearrange. I'm going to end up with 1/3 t1. So the time here is 1/3 of this time here. Okay, that's what we're getting. So where it says t2 minus t1 down here, I could just substitute in 1/3 t1. And that is what I'm going to do. And that way, my equation here now, -20, half times -12 is -6 t1. Half times 4 is 2, right? Times, and then t2 minus t1 is 1/3 t1. So 1/3 t1. And so I can see now I have an equation with just one variable this time, and I can go ahead and solve for t1. So this is like adding a fraction. So I get common denominator. So I'd multiply this by 3 over 3. So this would be -18/3 plus 2/3. -18/3 plus 2/3 would be -16/3. T1 is -20. Multiply both sides by -16/3. Negative signs are going to go away. I'm going to have 60 over 16 is T1. So your lowest terms. 4 goes into that 4 times. 4 goes into that 15 times. It'll be 15/4 seconds is T1. Or if you like, 3 3/4. 3.75 seconds is T1. Alrighty. Hey, that's not what I'm trying to find. I'm trying to find this whole time, T2. I want to find T2. And so I can take this value for T1 and put it back in here, right? Maybe, right? Here, I'll just go ahead and rearrange that. So, yeah. T2 then would be, I'd add a T1 over. It's 1/3 T1 plus another T1. That would be 4/3 T1. Multiply 15, well, I'll put 15/4 in because fractions work with fractions. 15/4 in for T1. So it's 4/3 times 15/4, right? When I put this value in. 4s will cancel. I'll get 15 over 3, which is just 5 seconds. And that's the value for T2. That's actually what I was trying to find. Okay. 5 seconds. Okay, now that I have that, can I find the acceleration? You say, sure, that's easy. I'll just put that into, I don't know. Well, actually, I know T1. Let's put T1 in there. So my A is 12 over T1. I could also put my values for T1 and T2 in this equation. That would be fine. But this one's easier. That's 15 fourths. So I'm going to have 12 over 15 fourths. When you divide by a fraction, multiply by the reciprocal. So that'll be 48 fifteenths. Whew. And 48 fifteenths, 3 goes into that 16 times. 3 goes into that 5 times. So 16 fifths, or if you like, 3 and a fifth, or if you like, 3.2 meters per second squared is my acceleration. All right, and that's that. Okay, so solving this problem again, we were using areas and slopes. Because it crossed the axis, we had 2 different unknown times, which gave us, when I solved the area, used the area for displacement, that gave me 2 variables for t, which is the difference from the first problem. Okay, I only had 1 time variable in this problem. I end up with 2. And so I need another equation, and I got that from slope is rise over run. We did something kind of tricky, recognizing the slope is the same here and here, so because it's a straight line, so the accelerations are the same. So I could set those acceleration expressions equal to each other, which is what I did here. Okay, that's it. All right, solve and use in the VT graph.